Let's talk about control groups. In this topic, we're going to look at what is a control group, just defining it, but we're also going to look at kind of the model and what it's sculpted to look like. We're going to talk about the rules that go into working with C groups, and then, of course, how do you actually administer a C group? So first of all, let's understand C groups. C groups are kernel control groups. They're a kernel feature that is designed to allow you to aggregate or partition tasks or processes together and affect those aggregations and partitions as a whole by executing a single command against those control groups. Now, tasks are by default organized into hierarchical groups, and that doesn't change within a C group. C groups can be configured to show the specialized behavior of what's going on or implement a specialized behavior as well. They can also be used to help in tuning the system to make best use of the available hardware and network resources based on the load and the work profile of that particular application or machine. So, some terminology that we need to define. First of all, a C group is the creation of an association or a virtual grouping of tasks with parameters for one or more subsystems. Those subsystems can be things like memory or disk or CPU. And we can set up a hierarchy where one C group is arranged as a subordinate to another one. And each process that is running is generally referred to when working with control groups as a task. So what is the C group model? When looking at the C group model, you have to understand what a process model looks like. Now, a process on a Linux system using systemd is going to be a child process of a common parent. So in this case, systemd is the common parent or the highest level process. Everything else is a subordinate or a child process of some nature below that. The Linux process model is a hierarchy and a single hierarchy where all processes descend from that single parent. And the Linux processes inherit the environment and other attributes from its parent process. So that's a Linux process. The C group model takes and allows us further division of that Linux process model into a C group model, where C groups are similar to processes in that they are hierarchical, and child C groups inherit the attributes from a parent C group. There is a fundamental difference between them, though, in that many hierarchies of C groups can exist simultaneously on a system, and when you interact with one of them, you don't necessarily interact with all of them. So multiple separate hierarchies are defined because we want to allow them the ability to interact with subsystems in a different way. Now, a subsystem represents a single resource. So when we talk about a subsystem in a C group model and modifying the way that a group of applications in a C group interact with a subsystem, we're saying something like the CPU is a subsystem, and this C group, let's call it C group A, interacts with the CPU, but only interacts with the cores 1 and 3. It doesn't interact with cores 2 and 4. And we can put the same kind of restrictions based on the type of subsystem we're working with, like memory. So when we're talking about C group design, the design allows for a simple C group usage. In other words, by default, it's simplistic. If you want to, you can make it very, very highly customized and make it work the way that you want it to work based on the needs of the applications and on that particular machine that you're configuring. So there are two types of subsystems when we're working with C group subsystems. We have the isolation and special controls, like allowing us to say CPUs 1 and 3 are being used, but CPUs 2 and 4 are not being used by a particular thing. We can work with network namespaces in such a way. We can do things like freezing and unfreezing various processes. And then we also have resource control, like how much CPU time is allowed within a C group. So we can say this group of applications is higher priority, therefore they're going to get more CPU time than other applications, and so on. So C groups give us control at a level both for isolation, but also for throughput and access to those application components. Here's a simple designation or graphic of what it looks like from a hierarchical standpoint when working with C groups. Now notice that this is all underneath the sysfs C group directory. We see underneath that a designation for C group, then the group itself, and any parameters and subgroups that might be affected by it. Here's another way of looking at it. If we look at the proc mounts file, cat proc mounts, and we grep for C group, it will show you the different C group items that are currently listed and available. So let's talk about those subsystems a little bit. What subsystems are there? There's the block I/O, which allows us to set limits on input-output access to and from block devices. We have the CPU subsystem, which is specific to the scheduler for providing task access to the CPU. CPU accounting, which allows us to give us reports on CPU availability, and CPU set, where we're assigning individual CPUs and memory nodes to tasks in a C group. We also have devices, which allows device hardware specific access to devices by tasks, and then the freezer, which allows us to suspend and resume tasks inside of a C group. We also have memory as a C group. How much information do we get, or how much memory do we get access to within a C group? And then we have network specific subsystems as well. So let's talk about the C group rules that might be used within the Linux C group environment. There are relationships between subsystems, kind of hierarchies of control groups and tasks. So we need to remember that system processes are called tasks in C group terminology, even though tasks may be in most cases relegated to items that are happening within a shell in a user world. So don't forget, system processes are still called tasks inside of a C group world. And there are 4 rules governing the relationships between the subsystems, the hierarchy of C groups, and the tasks themselves. Rule number 1, a single hierarchy can have one or more subsystems attached to it. This should be relatively obvious. If you're creating C groups, you are going to be putting them into a segregated environment where you allow applications within that to either have or restrict access to various items, such as memory, CPU, and so forth, those other subsystems we defined. Rule number 2, any single subsystem cannot be attached to more than one hierarchy if those hierarchies have different subsystems attached to it already. In other words, you can't do 2 at the same time. I think the graphic is fairly obvious here. Rule number 3, a task cannot be a member of 2 C groups in the same hierarchy. That doesn't mean they can't be in 2 different C groups of a separate hierarchy. And a single task can obviously bridge that. It just makes it so that tasks don't get confused and there's clear, obvious rules as to what access they have. Rule number 4 is that child tasks automatically inherit C group membership of its parent. It's then independent and can be moved to different C groups as required. So there are your 4 rules. C group functionality, however, you need to wrap your minds around the idea that a task can only belong to a single C group under a hierarchy, but once you move outside of that hierarchy, it can exist elsewhere. And several subsystems can be grouped together so that they affect all tasks in a single hierarchy. It is also possible to refactor a hierarchy. In other words, move tasks around and even move relationships between hierarchies in order to adjust the functionality within those C groups down below. So how do we administer C groups? We've defined our terms, we've set some rules now. What can we do and how do we do it? Well, C groups are administered by either creating subdirectories in the subsystem directories we defined under sysfs, or changing files in those subdirectories after we've created them. Now, systemd places each service into its own C group by default, and it's under a default hierarchy underneath systemd. The primary tools for administering C groups in SLE 15 are the mount and systemctl commands. However, there are other tools available. To view processes that belong to a service, the command is systemd-cgls, so list control groups. The mount command can be used to administer C groups using mount-t, talk to the C group, the group name, and then the location. The subsystems can be called individually with the mount command. None in this example is the C group name. The systemctl, which is a tool specific to interacting with systemd, can be used to set limitations on C groups, as systemd has inherited many tools inside of its environment for working with C groups, since it defines C groups for each of the tasks that are launched. Here are some examples, working with slices and services and defining our limitations based on the C groups that are inside of systemd.